Welcome to all. This is lecture 28. In that lecture, we will discuss how to expand a function of one or two variable by the help of Taylor or Maclaurin expansion. So first we discuss the Taylor's and Maclaurin's expansion for one variable functions. So what is Taylor theorem? The statement or say the Taylor series of one variable. Let's suppose we have a function fx of x which poses a continuous derivative of all orders in the particular interval exist. Then fx plus h can be expanded in the series of ascending power of h is what Taylor gives that series. Fx plus h can be written as is equal to fx plus h upon factorial 1 f dash x plus h square factorial 2 f double dash x h cube factorial 3 f triple dash x and so on. So here f dash x, f double dash x, f triple dash x shows the derivative of a function with respect to x one time, two time, three time. So here dash represent the differentiation of the odd order. Now if we put x is equal to a in that particular series, we say this is a equation number 1 and this equation is say the Taylor series. So if we put here x is equal to a in that particular equation or the series, so we get fa plus h is equal to fa h upon factorial 1 f dash a means the derivative of function at a h square upon factorial 2 f double dash a and so on. So this is equation number 2, which is the we can say is the deduction of the Taylor series or Taylor expansion. Now one more deduction. If we put in that equation 2, we say replace h with h equal to x minus a here. So what we get fa plus x minus a. So we get fx is equal to what? Fa here the h is replaced by x minus a f dash a plus x minus a square factorial 2 f double dash a and so on up to infinity. So there is one more expansion of the Taylor series, and this equation third is we use when we want to expand a function in terms of some factors. So we use that series. And the last one, if we put a is equal to 0 and h is equal to 2 in equation 2 here, if we put a is equal to 0 and h will replace with x, so we get a series fx is equal to f0, a replaced with 0 and h is replaced with x f dash 0 plus x square factorial 2 f double dash at 0 and so on. So that's equation number 4. This is a particular equation, and this equation or expansion is called Maclaurin theorem or Maclaurin series. So students, you have to remember here the first one, that one, this is a Taylor expansion, and by the help of Taylor expansion Maclaurin is expand and give a series that is in Maclaurin series. This is fx is equal to f0 x upon factorial 1 f dash 0. Here f dash 0 represent the derivative of a function at 0 and so on. So this is a Maclaurin series and that one is Taylor series. Now take an example. Expand the function fx is equal to e power x in the form of series. So most of you remember the series of e power x. So let's see how it has been expanded. So first we write the Maclaurin series. Maclaurin series. As you know, what is that? Fx is equal to f at 0 plus x factorial 1 f dash at 0 plus x square factorial 2 f triple dash at 0 and so on up to x power n factorial n f nth time derivative at 0 and plus so on, because the series is up to infinity. Now what we have to do, first we have to find the derivative of that function and find the f dash at 0. So here we have given function is what, fx is equal to e raised to power x. Now first we write f at 0. What we get if we put or replace x with 0? So we get e raised to power 0, and e raised to power 0 is what, 1. Now take the first differentiation f dash x with respect to x. What we get, again e raised to power x, and at f dash 0 what we get, e raised to power 0, which is 1. Again take the second derivative with respect to x of function fx. So again we get e raised to power x, and at 0 we get e raised to power 0, which is 1. And you see here, if we take the third derivative, again we get e raised to power x, and at 0 we get again 1. And in the similar way we can find the further order derivatives. Now put these values in that equation 1, means in the Maclaurin series. So what we get, what we do, we are putting the value of f0, f dash 0, f double dash 0, and so on in equation 1. So on the left hand side, that is a fx is what, e raised to power x, and f0 is what, 1, plus, now we write x upon factorial 1 into f dash 0 is what, again 1, plus x square upon factorial 2 into f double dash 0 is what, again we get 1, and so on. X cube we get factorial 3 into 1 and up to, and the nth term is what, x raised to power n factorial n. And the nth derivative, if you see the nth derivative in the similar way, what we get, the nth derivative of function e to power x is we get e raised to power x, and at 0 we get 1 and up to infinity. So you see here the expansion 1 plus x upon x plus x square by factorial 2 plus x cube by factorial 3, and so on up to infinity. So this is what, this is the expansion of that function, or we can say, sometime we can say the series of e to power x is what, is this. So in that manner we can expand any function. And you remember, if we want to just expand the function, any function, so we use the Maclaurin series, which is the extension of the Taylor series. Now see one more example. We have to expand a function fx is equal to log sec x in the ascending power of x. So we have to expand that function, or we can say we have to write the series of that function log sec x. So here let us assume that y is equal to, we have given log sec x, then what is the value of y at 0, means y0 here represent y at 0. Here this is what, this is the y, x is a log sec x, so we get log sec 0, and sec 0 is 1, so we write log 1, and log 1 is what, 0. So this is what we can say y0. Now what to do, we differentiate that function, so we write y1 here represent the first derivative. So what's the derivative of that function, 1 upon sec x into, and the sec x we get sec x 10x, so you just cancel, we get 10x. Now at 0, y1 at 0 means this is represent the first derivative at 0. So we get tan 0 and tan 0 is again 0. Now take the second derivative, that is y2. So what's the derivative of tan x is sec square x. So here you can do what you can write sec square as a 1 plus tan square x, and as you know tan is what, tan x, here tan x is y1, so we can write 1 plus y1 square. So what we get, we can say we get equation relation y2 is equal to 1 plus y1 square. Now if you put 0 at 0, so you write y2 at 0 plus is equal to, sorry, that's is equal to 1 plus y1 at 0 whole square. So y2 at y1 at 0 is what, 0, so we get 1 plus 0, we get y2 at 0 is 1. And in the similar way you can easily find the y3. Now take the y3, so at that time you just differentiate that equation y3, differentiate that equation, so what we get, y2 become y3 and the derivative of 1 becomes 0, and plus the derivative of y1 square, we write 2y1 into y2. Now at 0 what we get, y3 at 0 is equal to 2 times of y1 at 0 into y2 at 0. So here you already find the y1 at 0 and y2 at 0. So y1 at 0 is 0 into y2 at 0 is 1, so we get 0. So y3 we get at is 0. Now similarly we can find the one more term, that is y4. So for y4 we take the derivative of that term, so y3 become y4, and here you apply the product rule. 2 first function same, that is y1 into y3 plus now 2 y2 same and y1, the derivative y1 make y2, so we write y2 square. Now again you check the value of y4 at 0, so you just write 2 y1 at 0 y3 at 0 plus 2 times of y2 at 0 whole square. So here y1 is 0, so that term becomes 0 plus 2 into y2 at 0 is 1, so we get 2. So in similar way you can also find the y5 and so on. So what we get y1 at 0 is 0, y2 at 0 is 1, y3 at 0 is 0, and y4 at 0 is 2, and so on. So now what to do, we apply or we put these in the Maclaurin series. So first we write the Maclaurin series or extension, and that is what, yx is equal to what, y at 0 plus x upon factorial 1 y dash at 0, that is y dash means y1, because we are using the simple y1. Y1 means the first derivative of a function y, plus x square factorial 2 y2 at 0, y2 is there, the 2 time derivative at 0. Similarly x cube factorial 3 y3 at 0, and x power 4 factorial 4 y4 at 0, and up to infinity. Now substitute the value of y naught, y dash naught, So we get y0 is 0 plus x upon factorial 1, y dash 0 is 1 plus x square by factorial 2, y2 at 0 we get y0 is what, 0, y1 is 0, so that is 0, that become 1 plus x cube factorial 3, and y3 at 0 is again 0, x power 4 factorial 4, and y4 is at 0 is 2, and so on. So after simplify, we can write here yx is what, log sec x is expanded, so we get a series x square by factorial 2 plus x power upon factorial, that is 4, you can write, and into 2 we get 12, or you can also write that is 2, and so on. So if you solve one more term, so you can write the other term of that series. So in that way you can expand any function by the help of Maclaurin or the Taylor series. Now take one more example. Here we have to expand the function log sine x plus h in power of h. So here we use by using the Taylor theorem or the Taylor series. So here first we observe that we have to expand the function what, log x. We have to expand the function, let's say fx is equal to log sine x plus h in power of h. Means when we obtain the series we get the power of h. So here if the function fx is we can say sine x plus h, so we denote this is not fx, we write that is a fx plus h. The function is what, x plus h. Now if the function fx plus h is log sine x plus h, then we can say, or we can let fx is what, fx is log sine x. Okay, now fx is log sine x and fx plus h is log sine x plus h. So we have to expand the function. Now we have to expand fx plus h. So if you remember the Taylor's theorem in term of h. So we write what, we write fx plus h is equal to fx plus h f dash x plus h square by factorial 2 f double dash x plus h cube by factorial 3 f triple dash x and up to infinity. So here we have what, function fx is what, log sine x. So first we take the first derivative, second derivative, third derivative. So the first derivative of that function is what, f dash x. Log sine x, we get 1 upon sine x into, and sine x, derivative of sine x is cos x. So we write cos upon sine, we can write cot x. Take the second derivative of the function fx. So the derivative of cot x is minus cos sec square x. Now again take the third derivative also, fx. Now the cos square x, we write 2 cos sec square x into cot x. And in similar way you can also find the fourth derivative. Now substitute these derivative in that equation. We can say this is 1 in the Taylor expansion. So we write f x plus h, we get fx is what, log sine x plus h into the first derivative, we get cot x plus third term h cube by factorial 3 into the third derivative is what? Second derivative is what? Minus cos sec square x. So we write minus cos sec square x plus h that's a term h square upon factorial 2, and the third term is h cube by factorial 3, and here we write 2 cos sec square x into cot x, and so on up to. So here this is a expansion of log sine x plus h. So this is the expansion of that function by using Taylor series or in the term of power of h. Now take an example. Here we haven't given a function f(x) x cube plus 8x square plus 15x minus 24. Now here we have to calculate the value of f11 by 10 by the application of Taylor expansion. So here without using calculator we can evaluate the value of that function. So how? By using the Taylor expansion. How? Here we know the Taylor theorem or Taylor expansion. Taylor expansion is what? F x plus h, we get fx plus h f dash x plus h square by factorial 2 f double dash at x, and so on. So we have to find f 11 by 10, the value of function at 11 by 10, and that can be written 1 plus 1 by 10 in that form. So put x is equal to 1 and h is equal to 1 by 10 in that Taylor expansion. So what we get? We get series of, we can say 11 by 10 or 1 plus 1 by 10, the expansion of that function. We write f at 1 by 10, that is h, f dash at 1 by 10 whole square into 1 by factorial 2, f double dash at 1 by 10 cube 1 upon factorial 3, f 3 time derivative at 1, and as you know the function is of degree 3, so the fourth derivative becomes 0. That's why we expand that function up to the third derivative. Now find the function. We have given a function is what? X cube plus 8x square plus 15x, that is minus 24. Take the first derivative here, 3x square 16x plus 15, that's the second first derivative of that function. Now take the second derivative, we get 6x plus 16, third derivative is 6 and the fourth is 0. Now f at 1, we find the f at 1, so we put the 1 plus 8 plus 15 minus 24, we get 0. F dash at 1, here 16 plus 15 plus 3, we get 34. F double dash at 1, 16 plus 6, we get 22. We just substitute, replace x with 1, and f 3 time derivative at 1, we get 6, and the fourth derivative we get 0. So substitute that value in that equation, says 2. So what we get? F 1 plus 1 upon 10 is with what? F1 is 0 plus 1 by 10, f dash 1 is 34 plus 1 by 10 whole square, we get 100 into 2, we get 200 into f double dash 1 is 22 plus 1 by 100 cube, we get 1000 into 6, we get 6000 into f3 time derivative, we get 6, and as you know the 4 derivative and higher order becomes 0. So now evaluate this. So we get 3.4 plus that is that we get 0.11 plus 6 divided by 600, we get 0.001. Now add this, we get 3.511. So that's a value of f 11 by 10. So this is a simple application of using Taylor series. Thank you. Thank you. In the next lecture, we discuss the Taylor and Maclaurin series for the two variable.